All right, hey everybody. Hope everyone's doing well. This is another movie about sentential derivations. This time we're going to be working from section 9 of the slideshow number 16. So indirect derivation is the title of this section that we're going to go through in this video. And so what we're going to do here is introduce a new derivation technique. So we've got two derivation techniques so far, DD and CD, direct derivation, where you just directly prove what you're trying to show, and conditional derivation, where you get to assume something and then try to show so that something else follows from that to show that a conditional is true. We've got one more style of derivation that's going to really help make our lives easier, and that's called indirect derivation. That's what we want to talk about today. So to introduce it, consider an argument like this. It says premise 1, if P then Q. Premise 2, if P then not Q. And we want to therefore show that P is false, that is not P is true. It's not really clear how you could attack this argument. First of all, before we get into it, first of all, this argument is valid. I'm not going to show you that it's valid, but it is valid. We could do a truth table for it and figure out that it's valid. So we must have a derivation for it. There must be a way to derive it. We know that from what we did in the last video on soundness and completeness. But it's not obvious how to really go about proving this, because there's not a real obvious way to break down either of 1 and 2 to get not P. So here's the basic idea behind indirect derivation. It's going to use a really powerful style of proof technique, sometimes called reductio, sometimes called proof by contradiction. And the idea is this. Look, we're trying to show not P. So let's assume the opposite of that. Let's assume that P were true and show that that assumption can't be maintained. Why can't that assumption be maintained? We're going to show that that assumption can't be maintained because that assumption leads to a contradiction. And we know that contradictions are never true. So we're going to try to show that even though we're trying to show not P, ultimately, we're going to assume P, show that P leads to something that is definitely false, a contradiction, and that will suffice to show that not P is in fact true. That's the basic idea. And so here's how indirect derivation is going to work more formally. When we have a show line of any form, either P or not P or any complicated formula, you can try indirect derivation. What that allows you to do is write immediately after the show line, you're entitled to write the opposite of whatever your show line is. So if your show line is negated, in this case it is, we write down the opposite of that, P. But if your show line didn't have a negation, you could write down the negation of the show line. So we want the exact opposite of the thing we're trying to show as our assumption. So indirect derivation says you're allowed to assume the opposite and then immediately after that attempt to show a contradiction. And so we're going to come up with a special symbol that sort of represents a contradiction, because it doesn't matter what contradiction you derive. It doesn't matter whether it's P and not P, Q and not Q, whatever you'd like. It just has to be some contradiction. And so we'd like to have a symbol for that. And we're going to use this sort of double X sort of symbol to stand for a contradiction. Okay, that's how we go about setting it up. Now let me introduce two new rules having to do with the contradiction that will help us finish this proof. The main rule that we're going to use is what's called contradiction in. Contradiction in looks like this, and it's on your rule sheet. It says, if you have a formula A, and you have the negation of that very formula, not A, you can then write down a contradiction, and the designation is X in, or Xi. And so just to be clear, here's an example where you could do contradiction in. You've got P and not P. But here's another example where contradiction in would apply. P or Q and not P or Q. In both cases, we've got a formula and the negation of that formula, and contradiction in says you can write down a contradiction once you find something like that. Like I said, that's the main rule we're going to use, contradiction in. You'll note on our rule sheet there is a contradiction out rule. I'm not going to go through that here. It turns out you don't need it a whole lot. But if it comes up, if you have a question about it, please let me know. But just for the sake of sort of making things as clear as possible, I'm just going to focus on contradiction in here. Okay, let's see how that helps us finish this proof now, this derivation. So we've assumed the opposite of what we're trying to show, and we're trying to show a contradiction. So how can we do that? Well, look, from P and P arrow Q, we can get Q. That comes from 1 and 4 by arrow out. And from P and P arrow not Q, we can get not Q. That comes from 2 and 4 by arrow out. But now we appeal to our contradiction in rule. We've got a formula, in this case Q, and its negation, not Q. So contradiction in says you can write down that little x. That comes from 6 and 7 by contradiction in. And now we've essentially finished our proof. We've essentially finished our derivation. All we need to do is finish up notating our show line. So we showed a contradiction. What kind of derivation of that did we do? Well, since we're trying to show a contradiction and it's at the bottom of our proof, that's a direct derivation. So we cancel and box. And the notation here is ID for indirect derivation. Because the assumption that P led to a contradiction, we know that P can't be true. And if P can't be true, it must be that not P is true. That is, if P is not true, then not P is true. That's the basic style of derivation. So we cancel that and box everything below here. And that's indirect derivation. Now in the next video, I have a bunch of examples I go through, kind of walking through how this works in practice. But let me just say one thing about indirect derivation here before we finish. First, it's a lot like conditional derivation in that it entitles you to an assumption. That is, you've got a show line, an assumption, and then another show line. But unlike conditional derivation, it applies in any case whatever. So conditional derivation only applies if your what's in your show line has an arrow as its main connective. Indirect derivation works in any case because you can always assume the opposite. For that reason, it's an especially powerful derivation technique. While you never have to use indirect derivation will always work. It might not be the simplest, shortest derivation, but it will always work. So indirect derivation is nice to sort of have in your back pocket, if you will. So if you feel like you're stuck and you don't know what to do, try indirect derivation. All right, like I said, in the next videos, there's some practice problems, and you should also be working on these in the book and on the homework.